As a result of the climate change and seeing the effect of designing and living inside buildings that cannot stand against the outdoor climate and weather, people tend these days to design more efficient buildings in different ways that can protect them inside the building from the outside different conditions and to provide for them the best indoor environment that can enhance the performance, health, and to provide the thermal comfort. This enhancement can be done using efficient building materials, insulation, and one of the most efficient ways is applying the kinetic facade. The kinetic facade is mostly adopting different form transformation. It can be changing in rotation, scaling, translating, and movement. Many projects worldwide have adopted the kinetic facade techniques to enhance the indoor environmental quality, like Al Bahr Towers in Abu Dhabi and the Institute of Islamic Culture in Paris. Some kinetic facades concept can be driven from biomimicry from nature or even to mimic some historical facade elements like the mashrabiyya. The aim of the project. This project aims to study a building case in a temperate climate that has site constraints with a specific orientation and to show how to provide different solutions to enhance the indoor environment and the energy consumption. The methodology of the project is to select a site and analyze the constraints and the surroundings. Then, to provide a design of an office building showing how the internal spaces are affected by the site constraints and the outdoor environment. Then, to provide an efficient case following the local standards and codes. And lastly, to provide an optimized case that shows the enhancement done in the building elements. The selected site is in Sydney City, Australia, which is located below the equator. The selected site plot is located in Waterloo City in Sydney, Australia. The site location is surrounded by sports stadium, two parks, schools, and a hospital, and some residential areas around. The plot area is 2,400 square meter and the adjacent buildings on site. We have a warehouse, showroom, retail center, and a residential building. So the plot is surrounded by two main roads and has two axes, one for service and one for the main gate. Also, the plot has a small green park next to it. Weather analysis. The majority of the wind direction is coming from the west and south. And since the project is located below the equator zone, so from the sun path diagram we can see that the sun is coming from the north. The average temperature in summer it reached 28 degrees and in winter, in June, it reached around 10 degrees. The lowest global normal happens in June and the highest happened from November to March. The sun shading chart shows the majority of the time during the whole year the project location is located in the warm hot zone. And from the psychrometric chart, the comfort zone is between 20 to 23 degrees and the relative humidity is between 30 to 80%. Building design and the base case. The building type is an office building. It has a total BOA of 4,800. It is a ground floor, a +2 typical and plus roof. The daily operation hours start from 8 a.m. until 5 p.m. and the operation days from Monday to Friday. The main building components, back of house, entrance lobby, lounges, cafes, and the big portion is the office's workplace. The ground floor, it has around 50% of the office's spaces. The typical floors, the first and the second floor, it has almost 80% for the office spaces area. And the roof, we have around 30%, and this is mainly for lounges and cafe. Following the layout and the arrangement, all the offices spaces, they are facing the main roads and the northern elevation, where the direct sun is coming from the north. The focus of the study will be on the offices spaces where they are facing the north facade and the east facade, and a proper adjustment will be done on the facade to enhance the indoor air quality and the thermal comfort inside the spaces. The floor plans are designed from scratch following the plot boundary and considering the site limitations. The base case is considering a full glazed facade to enhance the outdoor view. Base case Suncast study. Solar energy calculation. From the output of the simulation, we can see that the solar energy mostly is very high during the summertime, starting from January until March, and it reached the lowest number during the winter in June and July. Northern and the eastern facades are the most facade sides exposed to the solar radiation. The roofs also it receives the most solar radiation since the roof is totally flat. The annual solar energy analysis shows that the northern facade it received 1834 kilowatt per meter square, and the eastern facade it receives 980 kilowatt by meter square, and the roof is receiving the most amount of heat, which is 1680. In the summer, the northern facade it receives 220, the eastern facade it receives 300, the roof 550. In winter, the northern facade it receives 314, the eastern facade it receives 91, and the roof it receives 280 kilowatt per meter square. From this comparison, we can see that the northern and the eastern facade they are receiving the most amount of solar energy. Thermal space condition for the base case. The base case will consider a continuous cooling and heating, since it's an office building and many machines and equipment they are installed already and should be operating at 24 hours. The base case also will consider the internal heat source generated from the computers and the people. The total energy consumed for the base case is around 475 megawatt hour for the offices, spaces, and the roof lounges. From the graph, we can see that the energy used for cooling during summer is higher than the energy used in heating during the winter time. The efficient case. The efficient case will use the base case results as a starting point and to develop the construction materials layers to reach a better energy consumption. As per the Australian Building Code Part 3.7.2, Sydney City is located in Climate Zone 6. The minimum R value required for the roof is 5.1 meter square Kelvin per watt, and the minimum R value required for the external walls is 2.8 meter square Kelvin per watt. Following the Australian Building Code, if we apply this on the IES software, the total R value for the external walls will be 2.8. The total R value for roof will be 5.1. The total U value for the worst case of the clear double glazed with minimum frame is to be 6.2. By doing the optimization in the efficient case and applying that on the construction layers for the walls, the roof, and the glazing. For the external solid walls, the EPF insulation thickness changed from 65 mm to 85 mm. And the external glazing, the cavity thickness changed from 15 mm to 20 mm. The roof construction layers, the PHF insulation thickness changed from 154 mm to 200 mm. This orientation test study shows two different rotation angles for the building, 90 and 180 degrees. By doing the simulation, the total energy generated has been reduced by 0.19 and 0.52%, which is low amount. This rotation test is difficult to be applied on reality, as the building has specific view direction and the access point we need to respect. From this test study, we notice that for the rotation two options, the 90 degree and 180 degree, the heating loads or the generated heats during the winter time has been increased. This actually has affected the total energy generated for the building. By running the simulation of the total energy consumption in the efficient case, the result is changing the insulation thickness in the roof, wall, and the cavity in the glazing has reduced the total energy consumption by 2%. This is compared to the base case. As per the lead requirement for the thermal comfort in the indoor environmental quality, the occupied spaces must follow ASHRAE requirements for the comfort zone. So by doing the optimization, we can reach the thermal comfort zone for each space and for the required temperature for each space. The optimized case. In the optimized case, the kinetic facade concept will be implemented on the exterior facade, mainly the northern facade and the eastern facade. And to achieve the best aesthetic look for the building, this also will be applied on the south facade. but with a variable numbers and parameters. The concept is derived from the honeycomb cells. The honeycomb has different solid and void variation that represent the fill and the empty cells. By mimic the honeycomb, an hexagon cell can be applied with the same concept of the closed and the open cells that are fully automated, following the sun direction that can increase the opening size to allow for more heat and light to enter the space, or to reduce the size to prevent and to reduce the external heat and sunlight. The cell design has different variations. It can have 80% facade open, or 50% facade open, or 25% facade cell open. This variation has been applied on the main facades using the BIM software. By applying the kinetic facade treatment, each facade has attractors and sensors that can follow the sun direction by increase or decrease the cell opening size to control the sun radiation and lighting entering the spaces. Some 3D views for the internal spaces, showing the facade effect on the internal spaces, the shadow effect, and to reduce the glare and the sun radiation. By applying different sizes and location and different configuration for the kinetic facade, by having 80% open cells and 50% open cells and 25 open cells, these open cells are parametrically distributed along the facade, and by doing the comparison between the three options, the results are as following. The optimized case 1 has total energy reduction of 5.4%. The optimized case 2, which has the 50% open cells, has a total energy reduction of 6.5%, and the optimized case 3 has a total reduction of total energy 7%. This is compared to the base case. From this comparison, an observation is noticed. The base case has less consumption for the heating during the winter time. This can be visually seen in June, July, and August. This is compared to the optimized case 2 and 3, where the heating cooling is a little bit higher. This is actually because of during the winter, the sun radiation cannot reach to warm the whole place. A comparison between the base case, efficient case, and the optimized case shows that the efficient case can reduce 2% compared to the base case, and the best optimized case, which is case number 3, has 7% reduction in the total energy. A comparison between the three different cases for the optimized case shows that it has 5.3% reduction and 7% reduction and 8.3% reduction. The biggest number is for case number 3. And also this comparison shows the amount of CO2 emissions for the three cases. The optimized case number 3 has 7.8% reduction, case number 2 has 6.8% reduction, and case number 1 has 5.2% reduction. This is compared to the base case. Project location and orientation is very important. It helps a lot in reducing energy consumption. However, any project can be optimized more and have better energy efficiency, enhancing the construction layers, changing the cooling and heating times, and also providing facade treatment. All these ways needs to enhance the internal environmental quality and reduce the total energy consumption.